A review of Criticality Accidents, Part 2, Mayak Production Association, 15th March 1953. Link in the description below. Plutonium nitrate solution in an interim storage vessel, single excursion, 1 serious exposure, 1 significant exposure. The accident occurred in a plutonium processing building. The plutonium had been recovered from irradiated uranium rods. After separation from the fuel rods, the plutonium in the form of nitrate solution was put through several purification steps. Operations were performed on 6-hour shifts, 4 shifts per day. The building was not equipped with a criticality alarm system. Following purification, the plutonium nitrate solution was routed through a staging area before being sent on for further processing. Operations performed within the staging area included mixing, dilution, volume measurement, sampling for plutonium concentration and purity, and interim storage. Plutonium solution that failed purity requirements was returned for further purification. The staging area consisted of a concrete cell and adjacent space located in the corridor outside of the cell. Figure 6 shows the layout of the concrete cell in the corridor. The staging area contained 15 identical short right circular cylindrical stainless steel vessels, each with a unique identification number. The vessels were 400 millimeters in diameter and 320 millimeters high, with the cylindrical axis oriented vertically. The staging area was not equipped with radiation monitoring instruments. Criticality control was implemented by a 500-gram plutonium mass limit per vessel. Criticality safety support consisted of part-time effort by a staff physicist. Operators were not trained in criticality safety. The 15 vessels were separated into 2 linear arrays. The first array, containing 7 evenly spaced vessels, was located near the back of the wall of the concrete cell. This array was installed on May 1952 and was supplied with solutions through permanently installed transfer lines. The concrete cell was 3 meters wide, 2 meters deep, and 2.5 meters high. Top surfaces of the vessels were less than 1 meter above the cell floor. Located in front of the array was a vertical 200 millimeter thick cast iron plate. In addition, a 125 millimeter thick cast iron top plate was located horizontally above the 7 vessels. This plate had cut holes above each vessel to allow access for making hose connections. Cadmium plates were positioned vertically between the 7 vessels. Procedures required that, for criticality safety purposes, vessels 2, 4, and 6 never contain solution. This constraint was expected to reduce neutronic interaction between the vessels. The second array, containing 8 evenly spaced vessels, was located in the corridor outside the concrete cell. The second array was installed after realization that the first array had inadequate capacity for the volume of plutonium solution being processed. Each vessel in the array was individually shielded by approximately 175 millimeters of cast iron on 4 sides and with concrete floor and wall on the remaining 2 sides of the vessel. The criticality accident occurred in vessel 18. Staging operations involved solutions being transferred between vessels in an array and between arrays. Vacuum transfers between the 2 arrays were performed by manually connecting hoses up to 7 meters in length. The vacuum system was located in a room adjacent to the concrete cell. To prevent plutonium solution from entering the vacuum system, a vacuum trap, located in the concrete cell, was used. This vacuum trap vessel was made of glass to allow for visual inspection. Procedures required that written instructions for each shift be reviewed by operating personnel at the beginning of the shift. A team of 2 or 3 people performed operations. Procedures also required that shift personnel review the result of solution sampling analysis. On Sunday, 15th of March 1953, the written instructions alerted shift personnel that 2 transfers of plutonium solution were scheduled to arrive at the vessels in the concrete cell. Table 1 shows the contents of the 7 vessels as recorded in the operation log before the accident. It should be noted that in violation of procedures, vessels 2 and 4 were in use, and the 500-gram mass limit was being ignored. A plan was prepared to receive the first transfer of plutonium solution. The plan specified that the contents of vessels 2 and 4 were to be transferred to vessel 18, which was located in the second array. The operational log showed vessel 18 was empty. Based on the values in Table 1 and the assumption that vessel 18 was empty, this transfer would result in vessel 18 having the solution volume and plutonium mass given in Table 2. Two operators performed the transfer of solution from vessels 2 and 4 to vessel 18. One operator was positioned next to vessel 18 and the other was in the cell near vessels 2 and 4. Following completion of the transfers, the operator next to vessel 18 disconnected the hose. Immediately after disconnecting the hose, the operator noticed foaming and violent gas release from the vessel. With his hands, the operator also observed that the vessel temperature was elevated, well above room temperature. The operator in the cell noticed that solution had accumulated in the glass vacuum trap. The operator in the corridor immediately reconnected the transfer hose to vessel 18. Both operators then decided to transfer the contents of vessel 18 back to vessel 4. The loss to the vacuum trap during the excursion explains why criticality did not reoccur during this transfer. Water and nitric acid were then added to vessel 4 to dilute and cool the contents. The operators then split the contents of vessel 4 by transferring it to vessels 22 and 12 located in the corridor. Neither of the two operators had any training in criticality safety, and neither recognized that a criticality accident had occurred. They did not expect that there would be any health effects, and they elected to not report their observations. They continued to perform the work of the shift by receiving 15.5 liters of solution containing 614 grams of plutonium into vessel 5. 2 days following the accident, 17th March 1953, the operator positioned near vessel 18 at the time of the accident abruptly became ill and requested medical assistance. An investigation was started after the operator reported his illness. The investigation determined that the operational log at the beginning of the shift on 15 March 1953 was in error. The contents of vessel 1 at the beginning of the shift was actually 10 liters of solution containing 448 grams of plutonium and not 15 liters of solution with 672 grams of plutonium. That is, vessel 1 contained 5 liters less solution than was recorded in the operational log. The investigation also determined that the missing 5 liters had been transferred into vessel 18 before the beginning of the shift. Table 3 shows the actual contents of vessel 18 at the time of the accident. However, the investigation was not able to determine who made the transfer or when it had taken place. As part of the investigation, both experiments and calculations were performed to estimate the conditions for criticality in vessel 18. The results determined that 30 liters of solution containing 825 grams of plutonium, 27.5 grams per liter, would be required for criticality. These values agree closely with the best estimate of the contents of vessel 18 at the time of the accident. 31 liters of solution with 848 plus or minus 45 grams of plutonium, 27.4 grams per liter. One contributing cause of the accident was the unrecorded transfer of 5 liters of solution from vessel 1 to vessel 18. The accidental excursion resulted in approximately 2 times 10 to the 17 fissions. This estimate was based on a temperature increase of 60 degrees Celsius in 31 liters of solution. The 60 degrees Celsius temperature rise was based on the coarse observation that the solution following the accident was at or near the boiling temperature. The accident caused no physical damage to any equipment. The operator positioned in the cell received an estimated dose of 100 rad. The operator near vessel 18 received an estimated dose of 1,000 rad. He suffered severe radiation sickness and amputation of both legs. He died 35 years after the accident. Procedures in place before the accident were unambiguous in specifying that vessels 2, 4, and 6 were to never contain solution. The presence of solution in vessels 2 and 4 at the beginning of the shift prior to the accident illustrates that procedures were being violated. The entries in Table 1 also show that the mass limit of 500 grams per vessel was being violated.